Welcome back to An Ape's Guide to Human Language. We are looking at speech sounds and speech categories, how they work, where we get them, and how they change. Our curious ape is wondering what it is that humans do to achieve the things we do with language. We're all apes. What makes their communication so effective compared to mine? So we've just learnt about phonemes, and we've learnt that our perception for speech sounds starts asymmetrical and is predominantly categorical in that we treat some sounds as more similar to each other than other sounds. We also know that across acquisition, the process by which we learn and change our perception of speech sounds is statistical, in that we accumulate evidence about how often we have heard certain combinations in comparison to others. And it's socially mediated, in that people are involved in our learning process. So our curious ape might be asking themselves, how is this similar to my vocalizations? Do I have categories in my speech, in my vocalizations? Do I or we as primates show learning trajectories? So the first data set we're going to look at is from baboons. So in this beautiful paper, researchers have taken the same analysis approach that we've seen already to the vocalizations of baboons and tried to figure out if they can find patterns among the sounds that they make that group together in ways that are similar to the way human speech sounds group together. So these baboon grunting sounds can be measured acoustically just like human speech. And we see here a measurement of F1, so the first formant that tells us how high or how low in the mouth the tongue is. And we see here F2, the measurement of how far bunched towards the front versus the back the tongue is. So exactly the same measurements that are used for human speech sounds being used to describe the acoustic space of baboons. And in this particular analysis, the researchers were able to pull apart a certain set of vocalizations from the possible acoustic space of baboons. And they see that for males, there are 3 different types of vocalizations that cluster together as a particular kind. There is one kind of grunt that is very sort of high and back-ish in the kind of tongue position that we might think of as being a bit like an ooh sound, although we're not seeing the measurement for the lip shape, so it could be quite different. There is a sound down here that's quite low, and it seems like there are 2 different targets here. This one's described as a wahoo. So we can see the ah open mouth, ooh, tongue further back in the mouth shape there. And grunt number 2, which is more like a sound. It's a bit higher up, a little bit more front. It's maybe not E that we would recognize, but heading in that direction. Female baboons make a slightly similar, slightly different set of grunts or sounds that can be distinguished. We can see here this green grunt 1, this blue bark. This is sort of in an lowish, frontish position, like in my variety of English. Sorry, this isn't, I'm saying it incorrectly already. This is more like an sound, like in my variety of English, cat. There is a backish sound here described as a yak, and a pink sound that they only make when copulating. Now, what's lovely about this paper is that they have mapped these baboon vocalizations onto acoustic space that would be possible for children who are speaking American English with those vowel targets. So we can see how the baboon vocalizations compare. We've already done a structure function analysis on some of the visible differences that we can see between different kinds of primate vocal tracts. So when we observe this vocal tract, we can notice that the available height within the mouth is less relative to the length. So this may have some acoustic outcomes on the range of speech sounds that are possible. We can also see that the velum here is very long and seems like it spends a lot of time in contact with the epiglottis, again, to prevent choking. Human velums don't go down as far as the epiglottis. However, it seems like, given the acoustic space available in the mouth, if this is what an American child who has a similar body size to this kind of baboon, given what an American English-speaking child could produce, we can see that there is a spread of sounds that cluster together in certain ways that seem to suggest that there is something that we can recognize as a little bit like our vowel categories in language. So, hey there, baboons, we have proto-vowels. I mean, it's true that baboons have less than humans, but this seems sort of vaguely familiar from all of the stuff we've been discussing. Vocalizations that fall into categories that have some kind of functional equivalence. What else have we got? Well, baboons also engage in a behavior known as lip smacking. And I have an example here. It's a bit tricky to hear, but we'll do our best. Now, we're not talking about the squealing of the younger baboon here, but rather those other vocal gestures, some of which are voiceless and some of which are voiced. So let's have one more go. We have some lip opening and closing at a particularly steady rhythm, and some of them are voiced. So let's have another go. So these ones are voiceless. Now, the researchers who've conducted this analysis have suggested that the rhythm that we hear in the that 5 to 8 hertz rhythm is kind of a little bit similar to how rapidly most human speech goes. And therefore, we might be seeing some kind of a linkage between the stress patterns of baboon vocalizations and what we see in our part of the evolutionary lineage. Ooh. So not only do we have proto-vowels, but our curious ape has an evolutionary possibility of proto-syllables. So the next question we want to ask ourselves is this like instinctual behavior, like crickets just rub their legs against their sides and make noise? They don't seem to need examples of somebody else doing it to copy, right? Is it just instinct, or is this something that is learned? So let's have a look at some learning trajectories. So we're going to hear some marmoset vocalizations. And I'm going to warn you before we begin, these can sometimes sound quite high-pitched. So be prepared to like move your headphones a little in case it is a bit uncomfortable. So we're going to hear infant number 1, a marmoset, at a few different ages. Or we're going to come back to this one in a second. Let's try infant 2. Yeah, we'll come back to this slide in just a moment. But let's look first at the spectrograms, because what we can see here in these representations of speech, of vocalization, is we have 2 different kinds of colored information. We have these like large blue areas that seem to be kind of very spread. So there's acoustic information from low frequencies all the way to high frequencies. And then we have some of these little patches that have tiny little stripes in them, where there seems to be a band of energy that is more steadily represented, but there are few of these compared to these. Now, this is at the first time point, 13 time point, I think these are days 36 and 60. So these are across ages. And we can see that those big smeared out vocalizations gradually get less and less until they're making this very consistent noise when they're a little older. And that seems to suggest like there might be a learning process involved. So I'm going to pause and make sure that I can play you those sounds because they're really interesting. So here we are resuming the lecture with the correct audio in, and we're going to hear how these different vocalizations change. Just a warning once again that some of these sounds can be quite loud, so watch out for your ears. My apologies. This time it should work. So we're going to hear some marmoset voices. And these are on different postnatal days. Postnatal 1, postnatal 13, postnatal 36, and postnatal 60 or thereabouts from 2 different individuals. Let's listen to that learning trajectory. So we can hear 2 different types of vocalizations, the one and the zip, zip, zip kind of one. Okay, let's listen to the other individual. So this individual is very similar. They're making some swit, swit, swit noises and some zoop, zoop, zoop noises as well. Let's see how this progresses over time. Ooh. So we're getting more of that zoot, 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 and less of that noise. Let's check in with our other individual. This is day 13 and day 14. So we're starting to get these longer calls that are and less of the zip, zip noises. Let's check in a few days later again, about a month later on, and watch your ears for this one. So we're getting less of the zrp, zrp, zrp noises and more of these long sustained. These are called the P calls. And also a little bit of this whistling noise as well. But I hope this is reminding you of what we heard about when we were thinking about our human babies earlier on, where they start off with some sounds that they make instinctively, like the crying for attention, the one that they need to do in order to make sure they get sustenance and don't get left alone. When others who can help them are perhaps moving around in the landscape more effectively than they are. So human infants make some noises instinctively, and then other noises, they're hearing other people around them say them, and they might try out using their articulators to try and try and approximate speech sounds. And then as time progresses, they become more and more aligned to the adult speech categories. So these are some much more mature vocalizations we're about to hear, and they do get quite loud. Oh. So we can see that these are now really well structured sounds that are very intentional and have like a vocal control modulation to them. Okay, that's enough of this guy. Let's hear the other one. Okay, again, lots of vocal control. So we've seen a transition between some early vocalizations that are very sort of poorly controlled and a little bit all over the place, and some others that have some beautiful articulatory control in them that are very well controlled. Is this learning progressing in a similar way? Is this something that we need adults in our environment to develop? Or is this something that we can acquire all on ourselves? Is this just something that happens with maturity? Or is it more definitely grounded in social interactions? So in the following study, we're going to look at differently reared individuals. We are focusing once again on marmosets, but this time we have a marmoset family. So we have a male and a female up here who have produced 5 offspring. 2 of the offspring over here are raised in the presence of the adults of their community. The other 3 are raised in isolation, so they never hear adult voices, or very, very rarely. So here we have the 3 individuals with the very limited parental feedback and the 2 who are normally reared. And what we can see along this trajectory is that those 3 who were reared in isolation from their parents with limited feedback from the parental voices, we can see that they're not developing the same sort of structured beep, beep that we were hearing before, right? So the normally raised kids, we see those patterns, those beautiful like pitch contours emerge. So this is the P call that we heard before. And we also, they've given us, the authors here, some examples of a few different other recognizable call types, including that twit, 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 trill type sound. And these are the kind of cry type noises that are the instinctive ones that very young infants make. So offspring 2 and offspring 3, we see there's a huge proportion of cries relative to the normally raised offspring 1 and offspring 2. And the P is not developing in the same way. And this is also true for offspring 3. Offspring 1 seems to be producing very few vocalizations in general. So it seems that if you are reared without input from a parent about the kinds of calls that your community makes, you don't progress along those statistical learning pathways, even if you are a marmoset. This is not something that is unique to humans. It is not something that is unique to human babies. And it's not something that's even unique to apes, because marmosets aren't even on that branch of the family tree. So it seems that the learning is indeed social, or at least based on the statistics of the individuals in our community. Can we learn something then about the social structure of the interactions? We're sticking with marmosets again for this one. And this is a wonderful set of studies that have been investigating the interactional dynamics of parents and children talking together. So here we have early infant-like, we've seen these babbling type articulations that have some cry type calls and some sort of pee, pee noises that are not very well structured. And the adult-like contact calls of older infants. And what the researchers here have done is they have looked in great detail at the timing of adult vocalizations relative to the timing of different infant vocalizations. And what they have found is that the timing of the adult calls is modulated by the timing of the infant calls. So when the infants produce a good P, good-ish P kind of structure, the adults will call back with a certain timing. So this is a reinforcement mechanism that the children are producing vocalizations that are socially salient to the adults, and the adults are in some way kind of encouraging their vocal development by giving them feedback of good examples of speech. This is turn taking. This is one of the first things that we see babies try to do in their, human babies try to do in their vocal interactions with adults, produce vocalizations that stimulate more speech, and then continue that feedback loop by keeping the conversation going. In fact, the researchers have also found that when the offspring give the wrong kind of speech or speech vocalizations at the wrong time intervals, the parents will just like not respond for a while. So there seems to be a rhythm for exchanging speech among marmosets. And if the kids get it wrong, if they like interrupt when a parent is talking, the parents will give them like a little bit of the silent treatment to wait until the next speech cycle is initiated so that they can have a better speech rhythm together. So this is a highly adaptive social vocal exchange. So we're not just talking about social learning in terms of the statistical experience you get by hearing others of your kind making vocalizations, but also we're seeing the mature primates of your species also adapting their speech in the presence of young who are learning to vocalize. This sounds very much like the primates in our own lineage and the way that they interact with their young. So this is dynamic social feedback. Great job, marmosets. It looks like many of the features that we might think of as being special about human speech, human vocal learning, and human social organization of statistical learning are features that we share with other members of our primate lineage. So we're going to have to look further into the linguistic behaviors and the communication types that we use before we'll be able to understand this question of what makes human vocalizations and human linguistic interactions able to achieve different jobs from the other primates in our lineage. So on that note, I will recommend a wonderful talk by Professor Patricia Kuhl, who did a great TED talk covering some of the details of the way that babies' brains are adapting to the acoustic environments of the adults around them, that you might find an enjoyable addition to the content of today's mini lectures. I hope you have enjoyed the curiosity of our curious ape, and we will see you back next week for our regular lecturing routine.